of the source language and the tokenizer of the target language. Now we can start building the model. So let's define a new method called getModel, which will, according to our configuration, our vocabulary size, build the model, the transformer model. So the model is, we didn't import the model, so let's import it. Build transformer. What is the first? The source vocabulary size and the target vocabulary size, and then we have the sequence length, and we have the sequence length of the source language and the sequence length of the target language. We will use the same for both. And then we have the dmodel, which is the size of the embedding. We can keep all the rest, the default, as in the paper. If the model is too big for your GPU to be trained on, you can try to reduce the number of heads or the number of layers. Of course, it will impact the performance of the model, but I think given the dataset, which is not so big and not so complicated, it should not be a big problem because we are not building a huge dataset anyway. Okay. Now that we have the model, we can start building the training loop. But before we build the training loop, let me define this configuration, because it keeps coming, and I think it's better to define the structure now. So let's create a new file called config.py, in which we define two methods. One is called getConfig, and one is to map to get the path where we will save the weights of the model. Okay, let's define the batch size. I choose 8. You can choose something bigger if your computer allows it. The number of epochs for which we will be training, I would say 20 is enough. The learning rate, I am using 10 to the power of -4. You can use other values. I thought this learning rate is reasonable. It's possible to change the learning rate during training. Actually, it's quite common to give a very high learning rate and then reduce it gradually with every epoch. We will not be using it because it will just complicate the code a little more, and this is not actually the goal of this video. The goal of this video is to teach how the transformer works. I have already checked the sequence length that we need for this particular dataset from English to Italian, which is 350, is more than enough. And the dmodel that we will be using is the default of 512. The language source is English, so we are going from English. The language target is Italian. We are going to translate into Italian. We will save the model into the folder called weights. And the file name of which model will be tmodel, so transformer model. I also built the code to preload the model in case we want to restart the training after maybe it crash. And this is the tokenizer file. So it will be saved like this. So tokenizer n and tokenizer it according to the language. And this is the experiment name for TensorBoard, on which we will save the losses while training. I think there is a comma here. Okay. Now let's define another method that allows to find the path where we need to save the weights. Why I'm creating such a complicated structure is because we I will provide also notebooks to run this training on Google Colab. So we just need to change these parameters to make it work on Google Colab and save the weights directly on your Google Drive. I have already created actually this code, and it will be provided on GitHub, and I will also provide the link in the video. Okay, the file is built according to model base name, then the epoch.pt. Let's import also here the path library. Okay, now let's go back to our training loop. Okay, we can build the training loop now finally. So train model given the configuration. Okay, first we need to define which device on which we will put all the tensors. So define the device. If I have CUDA on my computer, so okay, then we also print we make sure that the weights folder is created. And then we load our dataset. We can just take these values here and say it's equal to get ds of config. We create also the model. To get the vocabulary size, there is a method called getVocabSize. And I think we don't have any other parameter. And finally, we transfer the model to our device. We also start TensorBoard. TensorBoard allows to visualize the loss, the graphics, the charts. Let's also import TensorBoard. Okay, let's go back. Let's also create the optimizer. I will be using the Adam optimizer. Okay, since we also have the configuration that allow us to resume the training in case the model crashes or something crashes, let's implement that one, and that will allow us to restore the state of the model and the state of the optimizer. let's import this method we defined in the dataset. We load the file. Here we have a typo. Okay, the loss function we will be using is the cross entropy loss. We need to tell him what is the ignore index. So we want him to ignore the padding token. Basically, we don't want the padding token to contribute to the loss. And we also will be using label smoothing. Label smoothing basically allows our model to be less confident about its decision. So how to say, imagine our model is telling us to choose the word number 3 and with a very high probability. So what we will do with label smoothing is take a little percentage of that probability and distribute to the other tokens so that our model becomes less sure of its choices. So kind of less overfit, and this actually improves the accuracy of the model. So we will use a label smoothing of 0.1, which means from every highest probability token, take 0.1% of score and give it to the others. Okay, let's build finally the training loop. We tell the model to train. I build a batch iterator for the data loader using tcodm, which will show a very nice progress bar. And we need to import tqdm. Okay, finally we get the tensors, the encoder input. What is the size of this tensor? It's batch to sequence length. The decoder input is batch of decoder input, and we also move it to our device. Batch to sequence length. We get the to mask also. This is the size, and then the decoder mask. Okay, why these two masks are different? Because in the one case we are only telling him to hide only the padding tokens. In the other case we are also telling him to hide all these subsequent words, for each word to hide all the subsequent words, to mask them out. Okay, now we run the run the tensors through the transformer. So first we calculated the output of the encoder, and we encode using what? The encoder input and the mask of the encoder. Then we calculate the decoder output using the encoder output, the mask of the encoder, then the decoder input and the decoder mask. Okay, as we know the result of this, so the output of the model.encode will be a batch sequence length d model. Also the output of the decoder will be batch sequence length d model. But we want to map it back to the vocabulary, so we need a projection. So let's get the projection output. And this will produce a B, so batch sequence length and target vocabulary size. Okay, now that we have the output of the model, we want to compare it with our label. So first let's extract the label from the batch. And we also put it on our device. So what is the label? It's B, so batch to sequence length, in which each position so the label is already for each B and sequence length, so for each dimension tells us what is the position in the vocabulary of that particular word. And we want these two to be comparable, so we first need to compute the loss into this. I show you now. Projection output view -1 Okay, what does this do? This basically transforms I show you here, this size into this size, B multiplied by sequence len and then target vocabulary size. Okay, because we want to compare it with this. This is how the cross entropy wants the tensors to be. And also the label. Okay, now we can we have calculated the loss. We can update our progress bar, this one, with the loss we have calculated. And this will show the loss on our progress bar. We can also log it on TensorBoard. Let's also flash it. Okay, now we can propagate the loss, so loss.backward, and finally we update the weights of the model. So that is the job of the optimizer, and finally we can zero out the grad. And we move the global step by 1. The global step is being used mostly for TensorBoard to keep track of the loss. We can save the model. every epoch. Okay, model file name, which we get from our special methods. This one, we tell him the configuration we have and the name of the file, which is the epoch, but with zeros in front. And we save our model. It is very good idea when we want to be able to resume the training to also save not only the state of the model but also the state of the optimizer, because the optimizer also keep tracks of some statistics, one for each weight, to understand how to move each weight independently. And usually actually I saw that the optimizer dictionary is quite big, so even if it's big, if you want your training to be resumable, you need to save it. Otherwise, the optimizer will always start from zero and will have to figure out from zero, even if you start from a previous epoch, how to move each weight. So every time we save some snapshot, I always include it. State of the model. This is all the weights of the model. We also want to save the optimizer. Let's do also the global step. And we want to save all this into the file name. So model file name. And that's it. Now let's build the code to run this. So if name I really find the warnings frustrating, so I want to filter them out, because I have a lot of libraries, especially CUDA. I already know what's the content, and so I don't want to visualize them every time. But for sure, for you guys, I suggest watching them at least once to understand if there is any big problem. Otherwise, they're just complaining from CUDA. Okay, let's try to run this code and see if everything is working fine. We should, what we expect is that the code should download the dataset the first time, then it should create the tokenizer and save it into its file, and it should also start training the model for 30 epochs. Of course, it will never finish, but let's do it. Let me check again the configuration. Tokenizer. Okay, let's run it. Okay, it's building the tokenizer, and we have some problem here. Sequence length. Okay, finally the model is training. I recap you guys what I had mistaken. First of all, the sequence length was written incorrectly. There was a capital L here, and also in the dataset I forgot to save it here, and here I had it also written capitalized, so L was capital, and now the training is going on. And as you can see, the training is quite fast, or at least on my computer. Actually not so fast, but because I choose a batch size of 8, I could try to increase it, and it's happening on CUDA. The loss is decreasing, and the weights will be saved here. So if we reach the end of the epoch, it will